talks that are going to be related more or less vaguely to turbomachinery. And without further talk from my side, we are going to crack on with the presentations. And our first speaker has been in the consortium for quite some time, working as a postdoc with Paul Tucker. And I'm pleased to say that Zhong-Nan has now a permanent position at the University of Birmingham. So now is a proper member, I will say, of the consortium. So congratulations for your new lectureship. And today is going to talk about his work, of course, that he has been doing recently with Paul Tucker. And the title of the presentation is the most difficult word in English to say: Hierarchical Turbulence and Geometry Modeling of Fan Tip and Wake Flow. So please, Zhong-Nan, you have about 15 minutes, and then we'll crack on with the question.
Yeah. Thank you for the introduction. I'm Zhong-Nan. I work with Paul as a research associate at Cambridge, and recently take a lectureship at Birmingham. And the talk today, I want to present our work on hierarchical modeling of turbulence and geometries, mainly focused on fan stage flows. And the talk, I will go through 4 parts. So first, give a bit of information why we want to do this work, and the second, to introduce our methods. It's mainly on modeling the fan stage flow. It's basically, there are 2 parts. One is the Zonalised LES method, and the second, how to blending the mesh resolved geometry and the low order IBM methods. And finally, I give some results on the simulation and compare that with the experiment to validate our results. And finally, give a brief summary and outlook the future work. And the motivation to do this work is to simulate a fluid system with coupled components. One typical example of that is the fan stage flow. So you have the stator and the rotors, they quite coupled in the stage environment. And it's very challenging to simulate this flow at release Reynolds number. The difficulties come from 2 parts. The first is to resolve the substantial turbulence in the in this fan stage. So, for example, in our simulated operating condition, that is at the approach condition, where the when the aircraft is about to landing, and in that operating condition, the fan operates at half speed of the design speed. So the flow massive separated at the tip, and the separations tangled with the tip leakage flow from the tip gap, and also coupled with the shedding wicks behind the trailing edge. So it's quite complicated turbulence flows. So it's almost impossible to model that correctly using the RANS method. So that have been done using some high fidelity method like LES method. So another difficulty comes from the complex geometry. As you see in the fan stage, we have the rotor and stator, especially for this bypass fan stage. So you have 2 types of rotor, one sitting in the bypass and one sitting in the cold duct, which leading to the cold engines. So obviously the flows for this fan stage is not equally important. For example, in this half speed approaching conditions, flow separated in the tip regions, majority of the noise and the losses are generated in that region. So we mainly want to focus on these regions. So that comes the objective of the research. So our objective is to simulate these kind of flows with a hierarchical level of fidelity. So to be exactly, we want to model the tip regions with high fidelity, which is important in our research, and model the other parts use a low level of fidelity and blending them seamlessly in our simulation. So you might have been aware of that we have a hierarchy of modeling approaches in both turbulence and the geometry. And I think in turbulence, we are more familiar with. So we have this pyramid in turbulence modeling. So from the bottom to the top, we increase the part of resolving and decrease the modeled parts. And obviously, the cost of will increase from the bottom to the top. And if we want to express that in our Gamma equation, it's all incorporated in the viscous stress. So for the DS method, they model the parts of the turbulence stress is just the 0. But when we approach to the large eddy simulation, we model parts of the small scales motions using the subgrid scales, subgrid stress. And further down to the bottom, we have the runs method. We modeled all the scales of turbulence, and that come just into the eddy viscosities, and that is the runs Reynolds stress. And in between, we have the hybrid method, which hybridize the LES with the runs, and we can blending the two stress using a function which is f. This f is a spatial function. So, for example, in the classical DES method, this function is just based on the grid spacing, and in the DES, we want to model the whole runs layers using the runs, and the other part using large eddy simulation. That's a hierarchical modeling of the turbulence. And on the right-hand side, there's another pyramid, which is the hierarchical modeling of geometry. It's less common or less familiar to people. So we normally use the first one, which is the mesh resolved method. We resolve the whole geometry using mesh. And further down, we have the classical IBM method. We use the discretized body force to enforce the flows near the to recognize the geometry. And further down to the very bottom, that method is commonly used in the turbomachinery, which is the smeared geometry modeling. So we use the Admuso quantities through a turbine blade or the compressor blade, and we only model the flow turnings and the pressure rise or pressure change across the stage to get the right stage characteristics. And that is kind of reduced order modeling because we only modeled in 2 dimensions, and we kind of integrate over another dimension to get the average values of that. So here we call it filtered IBM methods. So we can also hybridize the low order geometry modeling with the mesh resolve modeling. Obviously, is similar as the hybrid runs and LES. So the work I introduced today is to use the both hybrid method for the geometry and the turbulence to model a fan stage. The fan stage we are looking at is a bypass fan. So the bypass ratio around 6 or 8, 6 to 8, but it depends on the operating conditions. And we choose to use the large eddy simulation to model the tip regions because the massive separation happens there, and the wake flow and the tip leakage. So, and this region is relatively important because the major loss is generated there, and also the noise is highly generated in these regions. For the downstream status, for the moment, we just use the low order modeling using the filter geometry IBM methods. So if we first look at the Zonalised LES methods, we blending the stress tensor using the runs method. We use this SAE method, and the LES method we use is the wheels for the subgrid stress. We just directly blending the viscous stress at this level, and the blending function is showing on the right hand figure. So the red part is the LES part, and the blue part is the runs part. You can see in the hub region the flow is relatively clean. We use the runs to model that, and for the separated region, we Zonalize the LES in that region. But if you zoom in towards the wall, you will see we have a very thin runs layers around Y plus 100 to model parts of the boundary layers. So it's like a well-modeled LES in a sense. So the bottom right figure just illustrates how that works out. So near the wall, we have the mean flow profiles resolved, and outside the y+100, we have the fluctuation resolved using the large eddy simulation. And you can see this kind of the trailing edge. After trailing edge, all the flow is resolved using large eddy simulation. And this kind of illustration how that works for our simulation. So this plane is just take after the trailing edge. So it's in the weak regions. So on the left-hand side is the eddy viscosity ratios, which is modeled eddy viscosity over the physical viscosity, which is molecular viscosity. You can see that modeled viscosity is mainly located in the lower parts of the passage. That's mainly because the RANS models model the most energies of the turbulence. So the eddy viscosity is much larger than that in the LES region. So the subgrid stress viscosity is much lower than the RANS eddy viscosity. And on the right-hand side is the figure we have for the viscosity magnitude. So in the upper part, we have the small scale structure resolved using large eddy simulation. And towards the hub, and you will see that reduce the scale of the flow, and they RANS only model the mean scales of the flow of the wake. So which we can see from the vorticity magnitude. And another component introduced in this hierarchy modeling is on the geometry. So for the downstream status, both in the high bypass and in the Kodak, we use the filter geometry methods. So the filter geometry method have basically three different types of the body force term. The first part is the blade normal force, which is the function is to turn the flows following the camber line of the blade to give the right flow turns across the stage, the stator actually. So another term is coming from it, which is the parallel blade force, which is viscous force. So this is some empirical correlations used to generate the right loss and the pressure rise using which incorporated in this term. And the last term is the S, which is we call it the blockage term. The blockage is due to the thickness of blades, which reduce the area of the passage. So we have three terms incorporated in the code in the body force and try to model the downstream status in fact. And that's kind of give us the potential field effect for the wake development. And a bit of illustrate how that works in the fan stage. So we have a fan rotor rotating in one direction, and the stator is just stationary. And from the fan stage, outlet of the fan blade at the trailing edge, and the V is the relative velocity if you're sitting at the rotation framework, and the U is the absolute velocity, which plus another rotating speed there. So after the fan stage, you can see the velocity is turning upwards because of the stator. So if you overlay these two vectors, you can see the swirl is taken out of the from the stator, which is turned that into the kinetic energy into the pressure. And if you see the relative velocity, and that also turn in the same directions. So it's actually increased the relatively tangential velocity. So on the right-hand side, I just show the simulation results. On the top is the simulation without any body force, and on the bottom is with body force. So in the body force region, I use the dashed line to indicate where the stator is sitting, and we simulate the flow in the relative framework, which is rotation framework. So the stator is actually rotated in the counterwise direction, in the opposite direction actually. So, and if you see the tangential velocity, I give the contour here. So after the stator is turning into the upward direction, which is desired. So it's see that function is try to turn the flows and give the right pressure rise across the stage. So we validate this method in a different rotor because there are detailed measurements in that stage, which is NASA rotor. We compare the total pressure, total temperature, and the flow angles at the exit of the rotor. And the rotor is modeled using the filter geometry IBM method. And we can see it can have a fairly good match with the experimental results using these low order methods. And then we use this hierarchical method in the stage fan simulation. And this low order method is mainly used for the stator, but for the upstream fan rotor, we use a mesh resolved geometry. And this kind of the overview of the simulations. So obviously you can see the flow scale changes in the span-wise direction. And in the tip region, which is the LES region, you can see the flow structure develops and resolved by the simulation. And for the bottom part, which is towards the hub, the wick is just resolved by the runs, which is with meaningful just give the mean shading of the vertices after the wick, so which is the typical scene in the run simulation. And if you zoom in, you can see the flow separation directly happen at the leading edge because of the high incident angles at the near the tip regions, and also the horseshoe vortex rolling up in the tip regions, and the leakage flow is hiding behind that. And because in our simulation, the fan tip gap is relatively small compared to the span size, so the tip leakage flow is not that strong, so it's just hiding behind the horseshoe vortex of the passage. And we compare our simulation with the experimental measurements just downstream the status, and the measurement is using the hot wire. And just before comparing the flows in detail, we check the operating conditions of our simulation. We check the actual velocity distribution radially, and that's match reasonable with the simulations. And we also check the mass flow in the bypass and in the conduct. So the error is just below 0.1%, so it's relatively small. So we can see the simulation is running almost the same as the experiment. So first we compare our result quantitatively with the experiment. And in the experiment, you can see a large variation from passage to passage. That comes to many reasons. One reason is the blade may be fluttering or vibration in this condition, and also the because the measurement is made using the hot wire. The hot wire also probably vibrates a bit, so you can see the variation of in the passage. And in the simulation, we just simulate one passage, so it's just axisymmetric. But obviously, you can see some similarities between the two. And we made another comparison on the turbulent intensity, and that's become more obvious, the passage-to-passage variations. And if you just focus on one reference passage, you can see the similarities of the LES and to the hot wire. So we will perform some quantitative comparisons, but we take this reference passage as a solid line, and we plot the variation of the passage as the arrow bar, and you can see how that compares with the simulation results. So the first result come here is the
Zhong-Nan, can you try to, we are at more than 20 minutes already, so can you try to wrap this? Thank you.
Yeah. So it's I almost finished. So I think this is just compare the simulation results. So basically, the main message is to match well with the reference passage and within the uncertainty regions for the actual velocity. And if you cross the interface of the runs and LES, and this is in the runs regions, and the simulation also match with the experiment result, but you can see the spreading rate is much less than the experiment, which is expected for the runs result. And also we compare the fluctuation components is matched with experiments within the uncertainty regions, and we're quite close to the reference passage. And the final conclusion is we develop this method and use for the fun stage, and it's matched with the experiment status within the uncertainty range. And the next step is we are currently running this simulation for longer sampling times, and for the analysis, loss generation, and the noise source analysis. And we also apply this method to a different configuration of the compressor cascade. We analyze the tip leakage flows dynamics. I think that's all from me. Sorry for delay that a bit.
Thank you very much.
Yeah.
If there's any questions, please use the chat, and Zhong-Nan will reply directly on the chat. So yeah, sorry, we don't have much time for questions. We need to move on to the next talk. So if I may ask you to stop sharing, and I will ask Chris Ellis to share his screen.
Yep, I will do.
Thank you. So Chris Ellis is working at Loughborough University with Gary Page and his supervisor Xia, I believe. And today is going to talk about mixing of hot stream and cold jet in an effusion cooling environment, impact of inflow turbulence. So please, Chris, it's your turn. Try to do your presentation in 15 minutes about. Thank you very much.
Can you see the slides?
That's perfect, yes.
Lovely, brilliant. Yeah, so as said, my name is Chris. I'm a PhD student at Loughborough University, working in the National Centre for Combustion and Aerothermal Technology. And today, it's not quite turbomachinery, but very relevant to the subject. It's we're presenting some results on mixing of hot and cold jets in effusion cooling environments, with a particular focus today on the impact of inflow turbulence. There we go. So first, I want to highlight a little bit of the background and motivation behind the work. Film and effusion cooling flows are very prominent in gas turbine systems through combustor liners, turbine systems, and their use enables improved efficiencies by allowing us to access greater temperatures in the combustor and turbines, as well as improving secondary air usage throughout the systems. But modeling such flows are rather complex. We have an image here by Frick and Roshko. This is quite a high velocity ratio flow, but you can see here that the flow structures are complex, and modeling these kind of flows with RANs is particularly difficult. So simple cost-effective RANs, they struggle to accurately capture these flows, not just simple two-equation models, but also explicit algebraic and even Reynolds stress models as well. On the right, you can see some figures that were produced that compare some LES data to a K-omega SST model for a low blowing ratio jet. And you can see here that the K-omega SST model, firstly, it fails to predict the centerline components of the cooling effectiveness across a surface. But more importantly, it doesn't predict this lateral coolant spread that is very important for assessing these flows and drives a lot of the overall cooling effectiveness. So this was inspired us to look into a simple two-dimensional flow, looking at common closure models in a simple two-dimensional separated heat transfer case, where we saw that there was lots of insufficiencies in these turbulent closure models. And that has inspired us to move on with data-driven and machine-augmented turbulence modeling approaches, where our essential aim is to output functional turbulent closures that better describe this mixing behavior in these range of flows so that it can be used in industrial cases. But one of the challenges here is producing very high fidelity simulations that accurately describe these flows and provide a robust set of solutions that we can drive these functional turbulent closures. So that has essentially inspired the work that we're talking about today, and looking at the impact of prescribing inflow turbulence on these flows to produce these high fidelity data sets that we can use for training and testing procedures. So now we're into the main aspect of the work. The environments in which we find these film and effusion cooling arrays have a very high degree of turbulent fluctuation. You can see in figure 2 on the right by Char et al. This is a plane taken between the combustor and the turbine. And these are the turbulence intensities. They're all very high and also spatially vary. So it's important to acknowledge these when we're looking at these kind of flows and assessing the impact on the cooling performance. And even in simple experimental analysis, like the ones that I'll be comparing to later, you often have the cooling holes within a developing boundary layer kind of flow. It might be laminar, it might be turbulent, and some experiments have free stream turbulence intensities associated with the wind tunnel. They also might introduce some to replicate the combustor environment further. And it's been shown in several papers that these high free stream turbulent intensities affect the cooling effectiveness quite drastically. And sometimes these are often overlooked when we do our computational experiments. So today I'm performing and showing you an assessment of 3 different turbulent inflow cases and their impact on the mixing of hot and coolant gas flow. So our computational setup is a single row of inclined plenum-fed coolant holes, but we won't be modeling an entire row. We're going to simplify the problem and model just a singular hole with periodic boundaries from side to side. We're comparing them to the experimental results of Sinar et al. And Pietri's paper. And we'll be using large eddy simulations with a wall adaptive local eddy viscosity subgrid scale model. These simulations have been conducted with OpenFoam, which is a little different to some of the work that has been shown in these previous presentations. But for us, it provides a suitable platform for us to implement these data-driven methods in a very simple manner and extend upon them. But also because it's an unstructured solver with some links to industry, we're able to address further geometric complexity when assessing things like turbine arrangements and combustor flows as well. We'll be using Klein's implementation, or an implementation similar to Klein's, of the digital filtering inflow turbulence to perform these assessments. And today, for most of the results shown, we'll be looking at quite a small mesh, 20 million cells, but our current work is looking at extending that to 80 million for even finer scales. So the 3 types of inflow turbulence that we'll be assessing today are shown on the screen. We firstly have a no inflow turbulence case. It's just a flat velocity profile, so essentially laminar, but this velocity profile is taken from the experiment, which is the developing turbulent boundary layer. The second is this boundary layer turbulence. So it's a developing turbulent boundary layer, and this is essentially what we're trying is mimicking the experiment. We have fluctuations that are described by the statistics within the experiment. So we have those correct turbulence statistics. And then we have the final case, which is a free stream turbulence case, where we have a 20% turbulence intensity provided through the mainstream with streamwise integral length scales that are approximately equal to the diameter of the coolant hole. And you can see here the variations in the flow as well. And now this third case, the free stream turbulence one, is mimicking that combustor environment where we see those very high elevated free stream turbulence values and turbulence intensities. Now, for seeking reassurance in our simple boundary layer turbulence case, we want to look at the oncoming profile and compare it to the log of the wall. As you can see, when we use a log of the wall, log law of the wall with a kappa of 0.41 and a C of 5, we're slightly above that value in the gradient. But when we look at the paper of McDonald and actually apply our adverse pressure gradient that we have just upstream of the hole, we match their results fairly well. So we can be reassured that our developing turbulent boundary layer prescribed by the digital filtering technique is of good quality for these CFD experiments. So the first set of results I want to present are the some plots of the adiabatic cooling effectiveness distributed across the surface. Now, this is a very effective way of measuring the cooling ability of such cooling arrangements. And so we don't have to do any conjugate heat transfer here. We're just taking the adiabatic wall temperature and essentially scaling it between 0 and 1 based on the free stream and the coolant temperatures. Now, first, I think it's useful to look at the left plot, which is the center line plots, as you can see by the diagram in the bottom right. It's noticeable that the no inflow turbulence case and the boundary layer turbulence case have very similar results, and they're very comparable to the experimental results of Sinar et al. But when we look on the other 2 plots for the laterally average distributions and the lateral distribution, you can see there are some major differences that start coming into play. So the boundary layer turbulence case actually does a good job of predicting the lateral averaged and the lateral distributions, which is what we wanted to aim for. We wanted to accurately capture the coolant spreads. So first of all, this is suggesting that introducing boundary layer turbulence is correctly exhibiting the right coolant spread that we need for these machine learning augmented turbulent model developments that we're pursuing. But by not considering inflow turbulence, you're drastically reducing that cooling effectiveness. And then we look at the free stream turbulent elevated case. We can see here that in the centerline results, there's a secondary peak in the first two cases, but not in this one. And that secondary peak is to do with at this blowing ratio, the jet is separated and reattached, which is why we get that secondary peak. But for this higher level of free stream turbulence, that doesn't occur anymore. And when we look at the lateral average, we actually have an improved cooling performance behavior over the first 6-7 diameters, which is interesting to point out. And then we look at the ACE maps. Some similar points can be illustrated, but it's nice to see on a qualitative level. But you can distinctly see that there is a clear impact on the lateral coolant spread between all three of these cases, with the lateral coolant spread increasing as the turbulence intensity develops. Now, hopefully you can see these two videos well. They're a little small, but they illustrate a couple of points. So this is taken on our baseline grid and essentially highlights the qualitative mixing. So you can clearly see here that the elevated free stream turbulence has a dramatic effect on the downstream performance of the coolant jet. But what's also important is the turbulence regime that's occurring within this very short cooling hole. The separated region provides a turbulent behavior that then progresses across that near wall trailing edge of the coolant hole flow. And as you can see, this is fairly consistent to about 3-4 diameters downstream, and then the elevated free stream turbulence takes over, and we'll see some of the effects on this later in the presentation. But it's also useful to look at the instantaneous flow structures, which are plotted here using the lambda 2 criterion, and we've isolated the coolant lambda 2 by essentially blanking the mainstream temperature to allow us to see a little bit clearly what's happening under the flow. So for the no inflow turbulence case, we can see that we have this instantaneous horseshoe vortex that rolls up ahead of the coolant hole and then turns around the coolant hole, and we get a little bit of transition as we progress downstream. But what's prominent here is the Kelvin-Helmholtz instabilities that manifest within the shear layer. They're very two-dimensional, and although this does break down into three-dimensional structures downstream, this is going to clearly have an effect on that lateral mixing between the hot and the coolant. Now, for the boundary layer turbulence, we have these incoming hairpin-like stretches that immediately impact with that shear layer, and that shear layer is essentially almost dominated by three-dimensional turbulence from the point of separation, which drastically drives the mixing. And you can see those three-dimensional structures progressing downstream. And with the elevated free stream turbulence case, we have these highly rotational structures, not just at the near wall and in the jet, but littered throughout of the domain. And that has a drastic effect on the mixing as well. Here we go. So to help understand the scales at which this mixing is occurring, we have pursued looking at the streamwise integral length scales, of which I've plotted a couple of the spatial correlation functions below, just to illustrate the difference in these functions that we use to integrate over to make the integral length scale. These are taken at 6 different profiles, which you can see outlines below the figure, and these correspond to the direct positions above the figure as well. So I want to point out profile 2, which is the trailing edge of the hole, x equals 0d. Now, across the 3 cases, these scales are almost identical to each other, although the free stream turbulence is slightly more elevated. And as we progress down in these profiles to profiles 3, 4, and 5, you can see that the no turbulence and the boundary layer turbulence integral length scales across these centerline profiles are very similar. And these are similar because they are directly influenced by that separated flow that we see within the coolant channel and near the wall that we saw within those earlier videos. And I guess the difference that we can see here is that when we look at the impact of inflow turbulence and when it comes into play, the rate at which these scales increase near the wall is the dividing factor between the 3 cases here. For the elevated free stream turbulence case, these increase fairly quickly to a point at 2.6 diameters downstream that they're almost the same as the inlet profiles shown on the very left. For the boundary layer turbulence case, this takes a bit more time to develop, and even at 10 diameters downstream, it's not quite the same as the free stream turbulence case. When we look at, so these are profiles taken at the same streamwise points, but 1 diameter off the center line in the lateral position. And we can see a couple of different things happening here. So for the boundary layer turbulence and the free stream turbulence case, we can see that the upstream scales are reflected in the downstream profiles, and even more so for the free stream turbulence case. At x equals 5d, the integral length scales begin to reduce for that boundary layer turbulence case as the coolant jet begins to interact with this profile. But the main message to show here are that the integral length scales that illustrate the essential scales of mixing are far greater for the boundary layer turbulence and free stream turbulence cases, and even more so for the free stream turbulence case, showing its ability to provide enhanced mixing of the hot and the cold gas. And we have a couple of plots to finalize our results of the turbulent spectra. You can see for the no inflow turbulence case at the point labeled position 1, we can see the reflection of the instabilities in the shear layer that we showed earlier. And when we take this into the frequency space, and the Struhal number is about 0.305, it has a big effect on the flow. The minus 5/3 slope is the one plotted in the dashed black line, representing the inertial transfer in the energy cascade. It shows some alignment for quite a wide range of wave numbers and varies between the profiles. But as expected, the elevated free stream turbulent case shows a greater intensities in the lower wave numbers of the spectra, reflecting the higher intensities of those fluctuations. And what's also useful to note, as we pointed out before, the near wall trailing edge behavior of the hole, which here is labeled as y equals 0.2d, it's position number 4 in those points. Those spectra are very similar. So we can see here that dominant behavior of the separation inside the coolant hole is similar for all 3 of these cases at this position. So to conclude, I've shown that digital filtering techniques have provided an effective way of providing an inflow developing turbulent profile. We've also shown through the first few plots of the adiabatic cooling effectiveness distributions that the inflow turbulence is critical to providing correct lateral coolant spread, which is what we need for our work in data-driven turbulence modeling. That incoming turbulent boundary layer is important in modifying the shear layer behavior and getting rid of those Kelvin-Helmholtz instabilities that we see. And we've also been able to show in the immediate integral that in the coolant plenum flow influences those immediate integral length scales at the whole trailing edge and in that near wall region for these cases. And increasing turbulent conditions modify the rate at which those integral length scales increase and their magnitude within the coolant jet. And our ongoing work, as I've discussed a few times within the presentation, we're going to analyze these results at a refined grid, as you can see by those videos on your right, investigating multi-hole geometries and machine augmented turbulence modeling these complex flows as well. But yeah, thank you for the time, and yeah, I'll open this up for questions. I hope I didn't go over too much.
Yeah, thank you very much. Well, we're just on the 20 minutes mark, so I guess we will use the chat. I have some questions, but I think we need to carry on to finish on time. But we are going to use the chat. So if you can have a look at the chat, I'm pretty sure you will have a lot of questions. But thank you very much for your presentation, and you have some very nice movies. It's quite nice to see. Thank you. So yes, so if you have any question for Chris, please use the chat. And we are going to crack on with our third speaker from Daresbury Lab, Jian Fang. And that's a very interesting timing, his talk, because Jian just won the UK Turbulence Consortium video competition. So I think I'm going to take this opportunity to congratulate him. I hope he's around, and I hope he's going to share his screen very soon. Yes.
Thank you, Siva.
Congratulations for this video, and I guess today you are going to present the work related to this video.
Yeah,
so
exactly.
Please share your screen and start your presentation.
Yeah, okay. Thank you very much. So today I'm going to present the recent DNS jobs of shockwave boundary interaction. This is a collaboration between Daresbury and Russian Academy of Science, where they took the measurements, and the University of West of England. For some background, as we know, the shockwave boundary interaction is kind of a main flow characteristics in hypersonic flight, and it's like a propulsion system or all types of shockwave boundary interaction. And among them, I think two most studied or most important ones are the impinged shockwave boundary reflective boundary interaction and the compression ramp, or the supersonic flow path forward-facing step. So previously we did some DNS of the impinged shockwave boundary interaction, including the one the award was given. So, but from that research, we have drawn a very important conclusion that the turbulence amplification is mainly caused by the flow deceleration related to the adverse pressure gradient, and not the commonly believed shear driven. So, we decided to further move on for the different geometry where there's a strong flow streamline curvature. So we just look whether or not the turbulence amplification mechanism will change or not. Is still the flow deceleration driven, or the streamline curvature have a notable impact or not? So we run a simulation with a flow over the forward-facing step with a different deflection angle, from the very small deflection angle 8 degree to 25 degree, which this 25 degrees is the kind of most studied one, and up to the 45 degrees. So they did the measurements of exactly the same geometry. So we run a DNS. So this is a flow parameter. We use the same height of the step. So the length of step will change. And this is the Mach number 2.9, the Reynolds number. So we run another DNS of a flat plate boundary layer to generate inflow turbulence, so we can reuse this inflow turbulence for different simulations. So that saves us a lot of time. So we use Astra code, and for the calculation of the convection flux, we use develop the legislative same-sort MP scheme, which have a very good performance and a high wave number. So it can resolve the small scale turbulence and also the shock wave. This is the mesh we use. So we use like this is the mesh size, and this is the size of domain. So we run basically a quantity 2D case. Use the homogeneous span-wise direction. So for the third case with a 45 degree step, we use a larger span-wise domain, because for that case there will be some like quite larger structures, but it provides even this extended span-wise direction is still not very big enough. This is a mesh resolution, and you can see we like turn the mesh gradually from the 90 degree to 45 degree in this case, so to ensure the smoothness of the mesh. So the mesh is quite fine. And this is first we validate our incoming turbulence result against some incompressible boundary layer data. So the red line is our DNS. So the blue line is the incompressible boundary layer DNS, and the black dot is a measurement also in the incompressible boundary layer. So the linear layer and the log layer of the velocity profile are well captured. So the Reynolds stress also good agreement with the incompressible boundary layer data, and also the turbulent kinetic budget is well balanced. So these dot are the balanced terms. So we can see which means all the dispersion are well resolved by our DNS. And then we first check the mean wall pressure. So this is 8 degree, this is 25 degree. The mean wall pressure are in a good agreement with the measured data. So we can see after the compression corner, the pressure is raised, and after the expansion corner of the step, the pressure drops. So basically, this is quite similar. So for the 8 degree case, we see that the pressure rise agrees with the Rankine-Hughes relation, and the pressure drop also can be well predicted by the Prandtl-Meyer expansion function. So for the 8 degree case, basically the boundary layer is acting like amplifier or not a damper, so smooth the pressure rise into a wider area. But the peak of the pressure is well predicted by the Euler equations. So for the 25 degrees is quite similar, but it's expanding in a wide area because there's a flow separation. So the signal will be propagated into the upstream for a longer distance. But still, I think the maximum pressure is also agrees with the Inflow theory. So you see that for the 25 degrees, we can see a lambda shock wave because there's a separation bubble there. So there's the one shock wave and the second. So therefore, the 45 degrees. So this is the result. So we can see the flow is largely separated, and there's also we can see the two shock waves. The one shock waves is the separation shock waves, and then the flow is separated and imping onto the face of the step. So there will be generated two shock waves. And for that case, the Euler solution is very different from the result from the Navier-Stokes result. So for the Euler solution, there's the one detached shock wave upstream the compression corner, and the pressure jump predicted by the Euler equation is way much larger than the Navier-Stokes. So so for this 45 degrees, the pressure rising is not determined by the Inflow theory, but also by a much more complicated the factors. And then we first check the goodies of the experiment. They have measured skin frictions and velocity profiles. So we also validate our DNS with the measured skin frictions. So they're all in a quite satisfactory agreement. So for the 8 degree case, there's no flow separation, and the 25 are quite a small separation, and for the 45 degrees, there's a very large, remarkable flow separations. So when we check the mean flow separation structure, we can see that for 8 degree case, there's the wall limited streamline are basically parallel, no three structures. The flow is essentially 2D. But for the 25 degrees, we can see the 3D structures of the wall limited streamline. And when we compare it with the experiment, so we see like very similar to a large Focky structures, and near the attachment line, we also see a quite strong 3D structures. So the distance between two Fockys is about the order of the boundary thickness. For the 45 degrees, the structure is very big, so we have to duplicate the domain in the span-wise, so that we can see two periodic structures, and the distance between these two critical points are like almost like 10 times of boundary thickness. And then we further check the velocity profiles. This is the position where they took the mean velocity. So also a good agreement between the DNS and the measurements was achieved. For the 25 degree also are quite good, but the experiment have quite a stronger separation velocity, but in the outside this agreement is good, and 45 the agreement is also very good. And then we check the turbulence amplification mechanism in these configurations. So first is the turbulence kinetic energy. So we see that for the 8 degree, we also see the turbulence kinetic energy is amplified near the corner, and 25 is amplified in quite a larger area. And we observe two peaks. One is above the separation bubble. The other is downstream of the reattachment line. For the 45 degrees, the separation zone is even in a wider area. So there we pick up the peak, local peak of the TKE, and then we profile this TK, the evolution of the TKE peaks. This X is normalized with the length of the stable. So we can see that for the 8 degree case, the amplification of TKE is quite limited, but then with the increase of the angle of the step, so we can see the turbulence kinetic energy is amplified in a much larger area. And interestingly, we see that for the 45 degree and 25 degree cases, the peak of the TKE is quite close to each other. But for the 45 degrees, we can see a quite strong second peak. So this is where near the place where the second leg of the lambda shock wave imping onto the wall, and cause it's like kind of another shock wave boundary interaction. And also very interesting, we noticed that there's the third peak after the expansion corner. This is quite out of our expectation. So then we try to give a little bit introduction of the idea of the study. So the amplification of turbulence is quite an important topic in the shock wave boundary interaction, because the first thing you notice is that turbulence become much stronger in the interaction region. So in the very early up to like the 21st century, there's a lot of theories to explain this. There's a linear interaction theory, the unsteady shock pumping, direct shock interaction, acoustic wave, entropy wave, and free shear. A different theory try to explain this, but then in the early 20th century, then with more like PIV and LES being involved in this study, people realize that the free shear layer, like this is show the generated free shear layer after the interaction is the main reason for the amplification of turbulence. However, in the recent research we conducted in the Daresbury, we noticed some fact that first the amplification of turbulence is mainly achieved in the near wall region, not the shear layer which is away from the wall. And then we noticed that the turbulence amplification is more correlated to the local acceleration rate rather than the shear. Then we decomposed the TKE budget, and we found the increase of TKE is due to the flow deceleration, these terms. So this is being recently published on GFM. So we give it like a different explanation of the turbulence amplification. We believe that in the early part, the deceleration of the mean flow is the main driven mechanism for the amplification of turbulence. Afterwards, when the shear layer is fully formed, then the shear layer take over the turbulence amplification and last quite a long distance in the downstream area. For this case, we try to conduct the same research, but we consider the streamline curvature effect. So this is the TKE protection terms. We noticed that the TKE protection distribution is quite similar with TKE itself. So we have a larger TKE protection and the compression corner area. Also in the expansion area, we have a very large negative TKE protection, which means there's a transform. There's kind of the reduction of turbulence energies. First of all, we try to decompose the TKE protection terms in curvature streamline. So we compose it into the streamwise deceleration terms and the shear-driven terms and the curvature terms. So this term is driven by the radius of the curvature. So then we try to study each how each terms act in the amplification of turbulence. So this is an 8 degree case. We noted this is a total protection. This is a shear driven. This is a deceleration, and this is the curvature driven. So we see that in this case, the amplification of a TKE is still mainly caused by the shear, and the curvature is one order lower than the other terms. So we give for the expansion corner area, the reduction of a protection, however, is mainly caused by the deceleration. So then we give the evolution of the peaks of each term. So we notice that the shear is still the dominant terms in the TKE protection, and the increase of shear terms is much larger than the increase of the deceleration terms. The deceleration terms is zero in the boundary because in incoming boundary because there's no pressure gradient. But then in the interaction region, the deceleration terms is still not as big as the shear-driven terms. So this is for the 8-degree case, the amplification of turbulence is mainly caused by the free shear. So the 25-degree cases, the situation is quite different. This is also the total protection. This is a shear, this is a deceleration. So we notice that the deceleration terms have a larger values in the initial interaction point, and also for the curvature terms, we still one order smaller than the other terms, but we notice that the curvature terms have a quite noticeable values and the edge of a separation bubble, because there's a strong streamline curvature there. So then we also extracted the peak values. So for this configurations, we see that the deceleration terms is much larger than the shear terms. So for 25-degree case, the flow is the amplification of turbulence is mainly caused by the flow deceleration, and also for the downstream leg of the lambda shock waves, the deceleration terms is increased again because you have a strong flow pressure gradient there, and also downstream the lambda shock wave, the shear terms is also start to grow. So the overall effect is the TK production is largely increased again after the reattachment. Then we follow we keep going on the 45 degrees. In this case, the flow have a greater curvature effect. So then we try to study also the different terms. So then there for this case, the deceleration terms is much larger than the other terms, and also things become very interesting near the expansion corner. So we see that the deceleration terms switch quickly from positive to negative, like here. So because you have like the quickly flow acceleration to flow deceleration to flow accelerations, and also we have quite the strong shear driven here in this region. Also, also interesting in the place where there's a strong streamlined curvature, the production of the streamlined curvature is not legislatable anymore. So we see like a noticeable contribution of a TKU production from the streamline curvature. So we concluded, so we did a series of DNS of a Mach 2.9 flow past a forward fin step with different deflection angle, and good agreements with the experiment data was achieved. So for the 8 and 25 cases, the pressure raise can be determined by the investor interaction theory, and the boundary layer acts like a damper of smearing the pressure jump, but the maximum of the pressure is determined by the Euler solution. For the 45 degrees, the pressure rise is quite different from the Euler solution, and the separation bubble acts like a low pitched step. So we think that might be the maximum pressure jump can be realized in a turbulent boundary layer. We're trying to figure it out. And then the flow in the 8-degree case is well attached, and the wall limited streamline present 2D pattern. For the 25 and 45 cases, the flow is separated, and the wall streamline present strong 3D characters near the separation and the reattachment lines. And then the amplification of turbulence in shockwave boundary layer interaction is dominated by the combined effect of shear and the flow deceleration. With the increase of the interaction intensity, the deceleration production become more and more significant. But for all the study cases, the streamline curvature production is not so dominated. But for the 45 degrees, we see the notable contribution from the streamline curvatures. Thank you very much.
Thank you very much, Jian. And well, it was 20 minutes as well, so we are just going to do the question via the chat. And you already have some question in the chat. So thank you very much. I just want to say that I will be putting the chat log with the video. So if people want to see the questions and the answers, it will be made available on the website along the video. Thank you again, Jian, and congratulations one more time for winning the UKTC video competition. If you can stop sharing your screen, then I'm going to ask the next speaker, Joshua, if you can share your screen.
Yeah, Yeah, I can do that.
Thank you very much. So Josh is working at the University of Cambridge with Andrew Wheeler, and his talk is about compressor tip leakage flows. So please, Josh.
Hi, can you see the slides? Just to
We can
check
see
first.
the slide and we can hear you very well.
Great, okay. Yeah, as Sylvain said, I'm Josh, and today I'm going to give you a short presentation on compressor tip leakage flows. The work shown in the presentation is completed by myself, Dr. James Taylor, Dr. Andrew Wheeler. We're all at the Whittle Laboratory at the University of Cambridge. The United Kingdom generates around 40% of its energy using gas turbines. Therefore, any increase in gas turbine efficiency results in a large reduction in CO2 emissions. Looking into the future, it's often proposed that gas turbines transition to burning hydrogen, and with the increased fuel cost that this brings, there's going to be an even more heightened emphasis on efficiency. Gas turbines are made up of three major components: the compressor, highlighted here in red, the combustor, and the turbine. Compressors are comprised of alternating rows of rotating and non-rotating blades. One of the largest sources of lost efficiency in a gas turbine compressor is the tip leakage flow. This can account for up to a third of the loss generated in a compressor. A compressor stage is made of two blade rows, a row of rotating rotors and stationary stators. Pictured here is a row of rotors. Blade rows have three main components: the hub, the blade, and the casing. If all goes to plan, the airflow flows around the blade and is turned by them, ultimately resulting in the pressurized the compressor is there for, and this is the main passage flow. However, it's important to note that there are boundary layers on the end walls of the compressor, and in addition to the end wall boundary layers, the blade surfaces also have their own boundary layers. For the rotors to do work on the fluid, they must rotate, and so must the hub they are attached to. This movement of the hub occurs at the base of the stators, which are themselves affixed to the casing. This necessitates the existence of a small gap between the stator and the hub end wall. The fluid moving past this gap is under the influence of the cross-passage pressure gradient. This forces some of the passage flow under the tip from the pressure surface of the blade to the suction surface. This is what we call the tip leakage flow. It enters the gap on the pressure side of the blade and exits on the suction side, interacting with the passage flow and the end wall boundary layer. Due to the different velocity magnitudes and directions of leakage flow, end wall boundary layers, and the passage flow, irreversible viscous dissipation occurs at the exit of the gap and far into the passage. This creates loss through a three-dimensional turbulent mixing process. And because of the issues accessing the geometry and complex flow topologies, experimental investigations into tip leakage flows are often difficult. Therefore, a high fidelity simulation is what's required to gain further understanding of this flow. To ground our simulation in the real world, we've matched the geometry and flow case to the Gibbons compressor at the Whittle Laboratory. The Gibbons is a 1.5 stage, low speed, 200% scale compressor. The rig is designed for rapid testing of different blade geometries. The image on the left shows the compressor with a section of casing removed so that the stators are visible. The compressor utilizes controlled diffusion blades for the stators, the tip section of which is shown here on the right. In precursor RAND simulations, it was found that only 30% of the span is required to fully capture the tip leakage flow. This allows us to simplify and reduce the computational domain. We have run two cases, one at 1.6% and the other at 3.2% tip clearance to chord ratio. At the top of the domain, we have used an envisaged wall to model the boundary with what would be the passage flow. The bottom of the wall is a no-slip wall, translating from pressure to suction side of the blade, as the hub would be for the stator. Measurements from the Gibbons compressor for total pressure and total temperature profiles are enforced at the inlet of the domain. Synthetic turbulence is generated to match the experimental values. We use a structured mesh with 1.6 billion cells, most of which are concentrated around the tip clearance. Using our high staggered topology, ensures low skewness at the critical gap suction side leading edge region. And the initial flow for the solution is computed using RANs, and 3 meshes were used to allow faster flushing of transients. So the flow cases are high fidelity simulations of cantilever compressor stators at 1.6% and 3.2% tip clearance to chord ratio. They were run at Reynolds numbers of 120,000 based on the chord for 17 and 12 tip through flows respectively. The mesh count for final grids are 1.6 and 1.8 billion, and they were both run on Archer at around 5,500 cores. To do this, we use Dr. Wheeler's 3DNS code. This is a 4th order finite difference scheme coupled with an 8th order filter. It has an explicit time stepping using 4th order Runge cutter scheme. As you can see in the figure, running the solver on both Archer and Archer 2 resulted in strong scaling for the real tip geometry case. The outputs of these simulations are 25 unstructured cuts and 4 structured cuts. The unstructured cuts are distributed along the chord, in the middle of the passage, in the tip gap, and on the blade itself. The structured cuts are at a constant span-wise height on the hub surface, at the middle of the gap, on the tip blade tip, and above the blade tip. Here you can see a contour of the ratio of cell length to Kolmogorov length in the middle of the gap. Most of the tip region is kept to values between 1 and 10. Regions of higher ratio are present in the passage flow where the mesh size is larger. The wall unit for both the hub and the tip is the Z direction, and as you can see from the table, the wall units in this direction are kept below 1. In the X plus and Y plus direction, the wall units are kept below 10. The final figure on the bottom right shows a spectrum for a probe in the free stream. The turbulent energy cascade is compared with the Kolmogorov -5/3 line in black. This data indicates that these simulations are somewhere around implicit LES. Hopefully the GIF is playing for all of you, and it shows a span-wise cut of the large gap height at 50% of the clearance. Contoured is radial velocity, normalized by the free stream velocity. The radial velocity is normal to this plane, and it's positive coming towards you, which is the yellow regions. From this cut, we can see the structure of the flow. The blue region on the pressure surface of the blade is negative radial velocity at the entrance to the tip. By the middle of the gap, this is turned into fluctuations of positive and negative values of radial velocity. These are large size fluctuations carrying out into the passage flow where they meet the passage flow of the compressor. The 2 main features of the flow after it has exited the tip gap are highlighted here. The tip leakage flow and the interaction of the tip leakage flow with the end wall boundary layer. The tip leakage flow is made up of the fluctuations noted exiting the tip gap on the previous slide. Where this flow interacts with the passage flow, a region in yellow of positive radial velocity can be seen at an angle to the blade. If we take a look at the tip gap on an axially constant plane, we can see that flow structure here is consistent with the span-wise cut. Radial velocity is now in the vertical direction. Flow from the end wall boundary layer enters the tip in combination with flow from the main passage. This is the region of blue at the left of the tip, indicating negative radial velocity. As it enters the tip clearance, the flow separates off the pressure side corner and fluctuates as it moves through the gap. After it has traversed the gap, tip flow exits at the suction surface and mixes with the passage flow. By zooming out, we can see that further into the passage, the tip flow interacts with the end wall boundary layer, highlighted again by the yellow region of positive radial velocity on the far right. And on this slide, I've plotted turbulent production at the top and turbulent kinetic energy at the bottom. The pressure side corner separation dominates the production in this plane, with lesser levels stretching further from the tip gap far out into the passage. High levels of turbulent kinetic energy are present also in the tip gap, close to where the production is high. There is also a region of high turbulent kinetic energy in the passage, in yellow again. This is probably what is referred to in the literature as the tip vortex. In this slide, I've plotted radial velocity for both clearance levels, sorry, at 50% of their respective gap heights. We can see the flow topology in the tip is similar, but not identical. The larger gap on the right shows bigger fluctuations across the tip clearance with a larger region of negative radial velocity at the entrance of the gap. The leakage flow emerges from the gap further downstream for the large clearance. Overall, we can see that a finer scale structure is produced as we reduce the gap size. This is true both inside the clearance and in the interaction region. The reduction in gap size also brings about a reduction in turbulent production and turbulent kinetic energy. For the small gap on the left, the shear layer breakdown inside the gap is still the dominant source of production, but is smaller compared to the larger gap. The turbulent kinetic energy is reduced both inside the clearance and in the passage for the smaller gap case. For both gaps, the pressure side separation shear layer is the dominant source of production. You can see this on both of the gaps with the top figures is the large, well, the very yellow portion. For these 50% gap height cuts, the production occurs further upstream for the larger gap. In addition, the reduced gap size has a smaller area of turbulent production. This, in turn, means a lower amount of turbulent kinetic energy in the tip leakage flow compared to the larger gap size. So, as a summary to conclude, we've completed an implicit LES simulations of compressor tip flows to match engine geometry and boundary conditions. This was done at engine representative clearance values of 1.6% and 3.2% tip clearance to chord. The flow cases show a strong interaction between the tip flow and turbulence in the end wall boundary layer. Oh, sorry. A reduction in gap height leads to finer scale structure in the tip flow and a subsequent reduction in the turbulent production and turbulent kinetic energy. And finally, the effect of turbulent flow structure on mixing remains to be determined, and that's where we're going with this next. So I think that's me done. Thank you.
Thank you very much, Josh. Very interesting presentation. We have a bit of time for questions. So if you have any questions, please put them on the chat or raise your hand if you know how to do that, or speak the truth. I had some question. I have one question. There is one question on the chat. What size of tip gap is compared to your incoming end wall boundary thickness, and how is that compared to the value for a real compressor stage?
So I think this is a question about the displacement thickness of the gap of the end wall boundary layer compared to the tip gap. It's I've got it written down. It's around 1.5 times the gap height for the small gap and half that for the big gap, because obviously it's 2 times as big. And compared to a real compressor stage, it should be the same as in the Gibbons, because that's what the inlet boundary conditions are measured from.
Thank you. Well, I have one small question about your numerics. So you said that those simulations are some sort of implicit LES. Yep. In your numerical schemes, do you introduce on purpose some artificial dissipation, or is there any specific treatment on this side?
No, it's just the filter for this one.
Just a filter.
Andy came on to answer that, but I think I may have answered already. Cool.
Great. And there's another question is, how many grid points do you have inside the gap?
Okay, so in the vertical direction across the gap, there's they're both around 200 points. There's, for the small gap, it's about 180, and for the large gap, it's 240.
Great. Thank you very much. I'm going to wait a few more seconds, but if there is no more questions, I would like to thank the 4 speakers today for very interesting presentations with very nice visualizations and very nice movies. So thank you very much. I also would like to thank you all the participants. I hope you enjoyed and you are enjoying those online talks. It's not as good as seeing each other in person and doing some networking and some discussions, but at the moment, this is unfortunately the best that we can do. So thank you very much for joining us. These talks were recorded, so I will put everything on the UK Turbulence Consortium website. I will add the chat so you can see all the questions and the answer. The video are going to be available. So if you are going on the UK Turbulence Consortium website, there is an online talks section where you will find YouTube links for all videos. So everything is on the UK Turbulence Consortium website, and the link is ukturbulence something, I can't remember, but if you do UK Turbulence, you will find all the links. Thank you very much, everyone. We are going to have the next series of talks. I think it's on the Friday, 5th of March. So I will be advertising about that on Twitter and via email. So thank you very much, and have a nice and relaxing weekend. And I shall see you very soon for other talks. Bye-bye, everyone.
Bye. Thank you.